Yeah, thanks. Thanks, Ravan. Okay, so I was thinking that today I'll take a chance to present a nice, interesting experiment which we did recently. Uh, it's not yet to the level of publication or anything of that sort, but I found these ideas interesting. So I thought that easiest way to learn would be to just present and just ask for feedback. So today I'll talk about high dimensional quantiles and distribution shift. So let's start with the basics. So if x is a simple one-dimensional real valued random variable, then we have a standard cumulative distribution function, which is simply defined as the chance that it's less than or equal to a particular x. But we can also define a quantile function, which is like an inverse of the cumulative distribution function, where we just take the infimum of all x such that such that the probability that it's greater than or equal to x would be at least p. So this is the definition of a quantile function. So this is standard. So having knowing the quantile function has several advantages. For instance, you can sample from the distribution because taking an arbitrary p will sort of give you a sample already, and you can easily compute the median because at p equal to 0.5 that gives us the median. But the first generalization would be, what about high dimensional random variables? How do these definitions extend? So the problem was there is actually no uniformly accepted definition which for the high dimensional CDF. So, and it entirely depends on the order in which you decide, in which the partial order you choose. So, for instance, the classic definition would be you take something called, I think, if x1 comma x2 is less than x3 comma x4, if x1 is less than x3 and x2 is less than x4. So in that case, we have this definition of a distribution function, and accordingly, you can also sort of define this. Oh, this is there is a mistake here. It should be p. It should also be p, not p1 and p2, just a single p. But the problem is this is arbitrary, and more importantly, if the probability is high dimensional, then we expect the quantiles also to be high dimensional. So one way to define this would be to observe the following. At a particular quantile level, you can actually get the quantile by minimizing a simple cost function, which takes minimize over x minus z times the quantile tau, 2 tau minus 1 times x minus z. So for instance, like the easiest way to check this would be if tau is equals to 0.5, then this is the mean absolute error. For different taus, we penalize different errors. Like if tau is greater than 0.5, the positive errors are penalized higher. If tau is less than 0.5, the negative errors are penalized higher, right? So one way to define high dimensional quantiles would be extend this entire optimization problem to high definition. So high dimensions. So if x is your high dimensional random variable, we define qx of u, where u can be anything with norm less than or equal to 1, as the minimizer of this cost, where these norms and the dot products and all are defined in high dimensions. So, so one thing to note is here U belongs to a unit ball in high dimensions, and the output is also in a high dimensional space, right? The same dimension as where X is defined. Now, why are we interested in this? So the thing is, there are several problems in the machine learning which require to know not just the output, but we want to know the distribution. Like if you want to identify the calibration properties, or if you want to identify whether it is out of distribution or not, these things requires us to actually identify what is the distribution of the data, not just whether if it's a cat or a dog. So, but the problem which I will talk about today is something called the distribution shift or data shift, and it's actually a common problem. So, essentially, what happens during distribution shift is if you have a pre-trained network on a particular data set, say cats and dogs, and with time, maybe due to evolution or something, say the cats or the way the cats and dogs behave change. Now, then the problem would be that the pre-trained network is useless. Like if the distribution shifts, then you cannot use the same network which you probably spent $1 million trying to train it. So this is a common problem in machine learning, and simple statistics actually doesn't talk about this much, but this has been a big issue with neural networks, and they're trying to solve this because this is a very practical problem. So let us define the formal problem statement of the distribution shift. So I have a particular sample coming from some input distribution on which my f theta is trained. And say I have, after some time, there is a shift in the distribution, and I have p plus, which is the shifted distribution. And I'm further simplifying the problem slightly by assuming that the way I label stuff is not changing. It's just that the input distribution is changing. But these ideas can actually extend to changing the way you label as well. But let's start simple. So the aim is we want to identify phi with the minimal retraining of my f theta. I don't want to change my f theta at all, but just identify phi, apply the phi appropriately, and then and then use f theta for the inference. So how do we do it? How do we identify phi? So the quantile loss. So we want to define something like a quantile loss for detecting distribution shift, right? So again, intuitively, if a distribution shift occurs, then the quantiles of the output should also change, right? Now, let's start with the naive approach. The naive approach would be if you have the one-to-one correspondence between the new samples and the old samples, it's pretty trivial to identify what is the distribution shift. But in general, we will never have this information. I mean, you cannot ask sample the same guy twice. And more importantly, it won't even be the same, right? So then how do you identify this? So the most important thing to note is that even if the individual, when you have a data distribution shift, then even though the samples are very different, the quantiles themselves don't change. So that's the core idea of identifying the distribution shift. So, and we want to use this to define our loss function. So the first principle which we have for I-dimensional quantiles is this identity, where suppose if your distribution changed from your initial random variable x to gx, where g is fixed but unknown, then the quantiles of gx at gu will match the quantiles at u multiplied by g. So that's what this equation simply states. So essentially for the right g, it should match the new one and the old, right? So if x plus is our novel new distribution, all I need to do is find a minimizer of this cost function, where each of the qx of u itself is also obtained by minimizing some other cost function. So
Aditya, this thing that the quantiles don't change,
yes,
is that is that obvious? It's not striking me as obvious, but then I don't know the enough to know that whether it is or isn't obvious. Why is it the
it's
case?
not technically that the quantiles don't change, but they change very predictively with the distribution shift. Like,
Okay.
so in the sense that, like, assume for the simple case that my entire distribution Just we add a constant to it, x plus c.
Ah,
Then
okay.
all
I
my
see.
quantiles also change
Oh,
x
see,
plus
I
c.
see. But when you say a distribution shift, you don't mean, for example, it can change from, say, a Gaussian to an exponential or some negative exponential or something, is it?
Uh, yes, technically it is possible, but we expect that um, it doesn't. It's something which we can still measure. Like if you change your Gaussian to exponential, that particular function will be very difficult to estimate with our simple neural networks. So so one underlying assumption which I'm making is that distribute the way the distribution shift happens, I should be able to recover it. I mean, if there is a
Okay.
chance. So, for instance, like suddenly, what if you know entire x changes to minus x? The
Mhm.
distribution entirely remains the same,
All right.
but it's not. We cannot identify it because the quantiles don't change for minus. Like if x is a Gaussian, x and minus
Mm.
x have the same distribution.
Right. Yeah.
So then the
So.
quantiles don't change and you can't identify it.
Mhm.
So I'm
Okay.
assuming that there is a way to identify this
Okay. All right.
feature. Yes. So so if I minimize, so if I do this, then technically I should be able to reconstruct the distribution shift if it is possible, right? So what we did is we started with a simple toy example to show this behavior. So we took a two moons data set in 2 dimensions and projected it into 100 dimensions using a Gaussian matrix 2 by 100. And we simulated a distributed shift by taking another Gaussian matrix of size 100 by 100. And we used the same optimization problem of 2 and 3 and checked if we can actually identify the distribution shift or not. So this is a simple initial experiment which we tried, and it turns out that we can. So if this was my initial two moons distribution, so for the sake of visualization, what I did is the I-dimensional data set in 100 dimensions. I projected it back to the 2 dimensions using the project inverse of the projection matrix, which I constructed too. So it's in my hands. So this was my original distribution, and this was the shifted distribution in high dimensions. And this was, I mean, we computed the G and then used the G to again shift the original one. And this is what we computed. While it's not exactly the same, we can already see that it's quite close by. I mean, at least the basic structure and all of it is preserved. So the initial results are promising. So we are able to again identify the distribution shift matrix pretty well if it is possible to identify it. But there is an interesting thing which we observe. Sometimes what happens is the G, depending on the random seed in the optimization procedure, there are initial condition. What we observe is we get a flipped version of it. And for some further analysis will allow us to see that at x equals to 0.5, around the line x equal to 0.5, what we have is an entire symmetry where the entire data set, like even if you shift the labels don't match, of course, but the data distribution itself is symmetric over x equal to 0.5. And so we conjecture that because there is one and only one such thing, we get two different minimizers to the optimization problem. One is the original one, the other is the flipped one. So we also are exploring another conjecture where we want to prove that the set of all minima of this quantile laws also captures the invariances in the data set. So this is another interesting observation which we observed from the simple toy experiment. So of course there are sorry. Of course, there are a lot of other things remaining. First, we still have to identify when is it actually possible to detect the distribution shift, if at all it is possible, and in what cases will it fail, and is the loss function. I mean, we again hypothesize that the loss function which we constructed is actually convex. So, I mean, we have to prove it. So, why is that the case? And this is still ongoing work. And yeah, so I think thank you for your attention. Any questions?
I'll wait till somebody else asks because I've already had a go. Um, so I have some questions about just the conceptual part of it, just as a thing, and then a question about um, how to use these results. Uh, so the conceptual question that I had was, is it the case that some kind of ordering is preserved in the sense that I mean, or is it the case that if some kind of ordering is preserved, you can prove some more serious, stronger results in the sense that, you know, suppose you have your original distribution and the x values um, were ordered in a particular way, where if you consider a partial ordering over the x values, say based on the fact that all these x values were, uh, you know, in some interval of, say, let's take, I don't know, some, you know, in the first decile or something like that, and then all these other next x values were in the second decile and so on. So is it the case that if the distribution was such that that these um, that ordering was still preserved, can you sort of, does something become simpler, or does that
Uh,
make sense as a question?
okay, so essentially, so what if my initial, so if there is a partial order on the my initial space,
Yeah,
then will
and that partial ordering uh, is preserved even with the distribution shift. Do you have anything stronger, perhaps, that you could say? Even
uh,
I don't know. I mean,
I don't I don't actually know an answer to that too. But there is one result which says that so these high dimensional quantiles, the way we are defining it as a minimization problem, as an implicit partial order defined within it. We just can't write it down explicitly,
hmm,
but it already defines an implicit partial order. So it's just that we just sidetrack the. I mean, ideally, what we do is we have the random variable, the cumulative distribution, and
hmm,
then the quantiles.
yeah,
And so this, the way this is formalized, sort of sidetracks it and shortcuts. I mean, it short steps the distribution construction of the CDF.
right, yeah,
But there is an
okay,
implicit condition there, which says, I mean, there is apparently some result saying that. There is an implicit CDF. You just can't do. You just don't know what it is.
okay,
Yeah, Aditya, as far as univariate statistics is concerned, I think, it is easier to establish partial ordering, but as far as, in a multidimensional setting, I think there is, arguably a lack of a natural ordering exists, right?
Yes,
So I we
but
don't have a
some.
straightforward answer to your question, Ashwin. But
yeah,
we believe, we just believe at this point of time that yes, there is some, you know, partially ordered quantiles which are, you know, probably, you know, sort of uh, invariant to transformations and things like that. And maybe that's what is doing the trick.
Okay, so now the second part of my question is more a practical question, which is that you motivated it by saying that there are uh, neural networks or whatever other kind of model that was built on a particular distribution, and then the distribution shifts, and then the network becomes unusable. Um,
Yes.
how I don't see at the moment you're providing any um, solution to that problem. Uh,
Uh,
is that would that be a correct
it's
understanding of your?
No, I think so. Essentially, to solve that problem, I mean, if we solve this problem well, assuming that the optimization and all of those kinks are settled, essentially replace x, the initial distribution, with f theta of x, and x plus with f theta of x plus.
Um, yeah, but how does
And
that
then,
tell you? Yeah, but
so
how do you sort of what you retrain or what?
so what we do is we add a couple of layers in front of the network, probably fully connected ones or something like very small ones, and train only the first two layers and make the remaining ones exactly same. That's the
Okay,
idea. So it's the
okay,
first two layers which are
okay, I
two or three.
understand. Yeah, interesting. Um, so now I have a sort of immediate pressing problem that I will be looking at next semester with Macquarie University, which is called a sort of domain adaptation problem,
Ah,
which they are facing, which is um, the following kind of issue, which is that, you know, so quite often, say, a model is trained at a particular hospital, and and it's doing quite well, but then you take it to a different hospital and it does really badly. Yeah.
yes,
Um, because not because anything has changed about the representation language, it's still the same set of features and things like that that they're using. But they use different equipment to measure it. Scanners are different, whatever. Um,
yes.
now, um, uh, this seems to be a kind of example of the kind of problem that you're talking about, no?
Yes, it's exactly that problem.
So, in principle, if we got some data from Macquarie, um, we should be able to do something for them, isn't it? In the sense that, um, from what you're saying, add these correction layers at the beginning and then use the same network should perhaps work. No?
Yes, in principle, it looks like I. So in principle, yes, but we still have to figure out the kink. Like there are a few kinks. Like optimizing this G is actually was pretty complex. So if the way we had to do it was something which is like first optimize on the initial distribution, then use those values on the other one, and accordingly adjust the constants in G and so on so that it works. So I hope I
Now
can.
some sort of neural hack will say that actually what you want to do is to uh, identify some abstract space where suppose you have these two domains, where say like these two hospitals,
Hmm.
you identify some abstract space where basically the features and the first hospital first features and the second hospital are both sort of in some way manifestations of that more abstract feature, and then you basically use those features as input. So in some sense, what you're proposing is it correct to say that what you're proposing is some principal way of identifying that abstract space rather than um,
Implicitly, yes. So we
rather
don't.
than just sort of hoping that this is the abstract space, rather, so typically,
Yes.
um, I'm not sure how they would do it, but I mean, I don't know, some auto encoding stuff would go on, I suppose, and something would happen where they would find some general generalized representation of the first set of data and the second. Okay, so now what happens when you don't have so the second, suppose when you do this domain adaptation problem, you go to the second hospital, you don't have the data from the first hospital, which is most likely the case. Yeah. So then what happens? You don't
Ah,
really have that data at all
yeah. If you don't have that, then it becomes.
because
Then this is not the framework which we should be looking at.
right.
Uh, I mean, in that case, actually, the only thing you can do is add a couple of layers at the start and try, uh, hope that if you optimize it, you will get an answer.
Okay, I see.
So, but the problem with that would be that will be shortcutting it, and it's not assured because you don't have the original network is trained on something, and if you
Mm,
add a layer before, and if you shortcut the distribution and all that,
mm,
then what happens is it tries to find the projection in which it gives a good answers
right.
on the training set. But the
Mm,
problem with that is it shortcuts it. Like it's not explanatory, or it
yeah.
doesn't generalize so well as the pre-trained one.
Right. Okay. Okay.
Aditya, I have a question from a non-CS person. So,
Yes.
can you hear me?
Yes, yeah, I can use.
So, it seems like the take-home message here is that you want to use this quantile optimization to reduce the training, right? I mean, so you don't want to retrain if there is a change in data distribution. Is that correct?
Minimal. I mean, not completely avoid it, but reduce it to as much extent as possible.
So just go back to what Ashwin was saying. So if at all, if the change in data distribution is minimal, it might work. But if at all, if it is like going from Gaussian to exponential, how useful it will be? Like,
Ah, it's so a couple of things. First, yeah. So as I said, like there are a couple of problems here. First is, I mean, not even x to Gaussian to exponential, but even x to minus x. That itself, I cannot do anything about it. All I will be learning is a simple identity function. So that itself I can't identify. So there are things which I can identify and which I can't. So an underlying hypothesis which we have is in high dimensions, this problem doesn't happen. Like in high dimensions, if there is a distribution shift, actually there is a shift in the entire support of the distribution, uh, not just, I mean, so the Gaussian and exponential example which you have given, the support is the same, in which means that it's the 0 to positive real numbers, it's entirely the same. The thing is, in high dimensions, the support itself changes. So, for instance, the classic example, I mean, this example we were looking at images where you had some sort of noise, like you have a simple image, you add raindrops or something of that sort. Then the entire image itself changes, right? And it's like an entire support. I mean, the entire set on which the high dimensional neural network is defined itself changes. So that is what we are trying to identify. So it's so in high dimensions that usually doesn't happen, and if it does happen, this method won't work.
okay.
So that's the again, yeah. In one dimensions, it doesn't. This hardly makes much of a sense because x and minus x itself, I can't do anything about it because it has the same quantiles. And I don't think there is any way you can differentiate between x and minus x, assuming that x is Gaussian.
Standard Gaussian is, yeah.
Yes, standard Gaussian, yes. Hope I answered your question.
Yeah, I think I have understood part of it. Thanks.
Yes, thank
There are no more questions. Are there any more questions from the audience? Okay, looks like there are no. Yeah. No. Okay. Okay. So thanks for the wonderful talk. So let's meet next week at the same time. Thank you all.
Thank you.
Great. Thank you.
Thank you.